Welcome everyone to the deep dive. And a very special welcome today goes out to Mr. Jager's students at Ishik Boys High School. Welcome to For the Love of Physics podcast. We are Mr. Jager's assistant. Today we're diving into something we feel all the time but maybe don't fully think about. Temperature and heat. What are they, scientifically speaking?
It's a great topic. And yeah, they're absolutely fundamental. Understanding them helps make sense of so much, from making a hot drink to why bridges are built the way they are.
Okay, let's unpack this then. You know that immediate feeling of hot or cold? Like you grab a glass of lemonade with ice, it feels really cold. Or a hot chocolate feels, well, hot and comforting. That feeling is our starting point.
Right, but what's fascinating here is how our bodies, our sense of touch, can actually trick us. It's pretty misleading sometimes.
How so?
Well, it depends a lot on your own skin temperature at the moment and also what the object is made of. There's that classic experiment, maybe you've tried it. Put one hand in hot water, the other in cold, and then plunge both into lukewarm water. That lukewarm water feels warm to the cold hand and cold to the warm hand.
Ah, right. So your perception is totally relative.
Exactly. It shows we can't just rely on feeling for a scientific definition.
So if our senses aren't reliable, what's the actual science? How do we define and change temperature objectively?
It really boils down to energy. Adding energy or removing energy usually changes temperature. Think about turning up the dial on an electric stove. You add energy, the element gets hotter.
Okay.
Scientifically, temperature is directly proportional to the average kinetic energy of the particles, the atoms and molecules inside a substance.
Kinetic energy. That's the energy of motion, right?
That's it. Add energy, the particles jiggle and move around faster on average. We measure that increased average motion as a higher temperature.
And these particles can move in different ways. You mentioned kinetic energy types.
Yeah, depending on the substance. For simple gases, it's mostly translational, just moving from place to place like tiny billiard balls bouncing around. But for more complex molecules, especially in liquids and solids, they can also rotate like a spinning top. That's rotational kinetic energy. And they can vibrate too, stretching and compressing their bonds, sort of like a spring. That involves both kinetic and potential energy.
So it's like a whole internal dance happening.
Pretty much. And all that energy combined from all the random motions of all the particles, that's what we call the internal energy of the substance. We often use a simple U for that.
And that's linked to temperature?
Directly. Especially for simpler cases like ideal gases. Internal energy is proportional to temperature. More motion, more internal energy, higher temperature.
Okay, that makes sense. Now, you mentioned temperature is only really meaningful when it's stable. What does that mean?
Right. Think about this example. You take a can of warm fruit juice, maybe room temperature, and you put it into a big bucket of cold water.
Okay, I can picture that. The juice will cool down, the water will warm up a bit.
Exactly. Energy flows from the warmer juice to the colder water. This keeps happening until what?
Until they're both the same temperature.
Precisely. They reach a point where there's no net flow of energy between them anymore. They've balanced out. That state is called thermal equilibrium.
Thermal equilibrium. So they have the same temperature and energy transfer stops, basically.
The net transfer stops, yes. Energy might still swap microscopically, but it's equal in both directions. And this idea is actually how thermometers work.
Ah, so when you stick a thermometer in your tea, you have to wait.
You have to wait for the thermometer itself to reach thermal equilibrium with the tea. The liquid inside stops moving when its temperature matches the tea's temperature.
Clever.
And a key thing about equilibrium, the final temperature will always end up somewhere between the initial temperatures of the two objects. The juice won't get colder than the water was initially, and the water won't get hotter than the juice was.
Right, it averages out, in a way.
Sort of, yeah. Settles in between.
Okay, let's shift slightly. Temperature changes things, like size. You mentioned bridges earlier.
Yes, thermal expansion. It's a really noticeable effect. Most substances, gases, liquids, solids, tend to expand to take up more volume when their temperature increases.
And the gaps in bridges are for that.
Exactly. Concrete and steel expand quite a bit on a hot day. Without those expansion joints, the immense forces would cause the bridge to buckle or crack. It's serious stuff.
Wow. And do different things expand differently?
Oh, definitely. Gases usually expand the most for the same temperature rise. Then liquids, solids expand the least, generally.
But you said generally. Is there an exception?
There is, and it's a super important one: water. Water behaves, well, weirdly near its freezing point.
How so?
Most things shrink as they get colder, right? Water does too, but only down to 4 degrees Celsius. Between 4 degrees C and 0 degrees C, as it gets colder, it actually starts to expand again.
It expands when it cools. That seems backwards.
It is unusual, and it means that ice, which forms at 0 degrees C, is less dense than the slightly warmer water below it.
Which is why ice floats.
Exactly. And it's why lakes and ponds freeze from the top down. The coldest water, at 0 degrees turning to ice, stays at the surface, insulating the water underneath. If water acted normally and got densest at freezing, lakes would freeze solid from the bottom up, and aquatic life wouldn't survive winter.
That's amazing. Such a small quirk with huge consequences.
Nature is full of things like that.
So how do we measure these temperatures accurately? Thermometers. You mentioned that they use expansion.
Right. Common thermometers contain a liquid, like mercury or colored alcohol, in a very narrow tube. That liquid expands quite a bit, even for small temperature changes. Because the tube is so thin, even a tiny increase in the liquid's volume makes the column rise noticeably.
Ah, it magnifies the effect.
Precisely. But to make sure everyone's thermometer reads the same, we need fixed points for calibration.
Like benchmarks.
Yeah. We use 2 easily reproducible temperatures. The ice point is defined as 0 degrees Celsius. That's the temperature where pure water and ice exist together in equilibrium at standard atmospheric pressure.
Okay, 0 degrees C.
And the steam point is 100 degrees Celsius. That's the temperature where pure water and steam are equilibrium, again at standard atmospheric pressure.
Boiling point, basically.
At standard pressure, yes.
Yeah.
So you mark 0 and 100 on your thermometer tube.
And then just divide the space in between into 100 equal parts, the degrees.
That's the Celsius scale in a nutshell.
And there are other scales too, right? Fahrenheit and Kelvin?
Correct. Fahrenheit is common in the US for weather and daily life. Celsius is the standard pretty much everywhere else and in science globally. And then there's Kelvin.
Kelvin sounds more scientific.
It is. It's the absolute temperature scale.
Yeah.
It's crucial in many scientific fields because it directly relates to the energy of particles. Remember how gas volume relates to temperature? That graph works beautifully with Kelvin.
And there are formulas to convert between them.
Yes, there are simple equations like TF -5 TC plus 32.0 to go between Fahrenheit and Celsius, and T plus 273.15 for Kelvin and Celsius.
Yeah.
But we won't get bogged down in the calculations today, just understanding the scales themselves.
Okay. What's special about Kelvin? You said absolute.
The big thing is that the Kelvin scale starts at 0 and only has positive values. 0 Kelvin is called absolute 0.
Absolute 0. Sounds intense.
It's the theoretical point where all random particle motion completely stops. It corresponds to negative 273.15 degrees Celsius. It's like the ultimate cold.
Can we actually reach it?
We've gotten incredibly close in labs, like fractions of a degree above it, but reaching absolute 0 itself is thought to be physically impossible. It's a fundamental limit.
Wow. Okay, so temperature is about the energy in a substance, the particle motion. But what about heat? You said they were different. Let's go back to the juice can in the water.
Right. Energy was moving from the warm juice to the cold water. That transfer of energy, specifically because there was a temperature difference, that's what we call heat, often symbolized by Q.
So heat isn't something an object has, like temperature.
Exactly. Heat is energy in transit. It's the flow. An object has internal energy, and it has a temperature, but it doesn't have heat. Heat is what flows between objects at different temperatures.
And it always flows one way.
Spontaneously, yes. Always from the higher temperature object to the lower temperature object. Like water flowing downhill, it naturally goes from high potential to low potential.
Okay, so microscopically, it's the faster moving particles in the hot object bumping into the slower ones in the cold object.
That's a great way to picture it. Those collisions transfer kinetic energy, warming up the colder object and cooling down the hotter one until
They reach thermal equilibrium.
you got it. At equilibrium, the temperatures are equal, so there's no net flow of energy as heat anymore. The transfer rate becomes equal in both directions.
So temperature difference is the key driver for heat transfer.
Absolutely. The amount of energy transferred as heat depends on that temperature difference. A bigger difference means a faster or larger transfer over a given time.
Like the example of raindrops on a car. If the temperature difference is the same on a hot day versus a cold day,
Then the initial rate of heat transfer from the car to the raindrop would be similar, even though the actual temperatures are very different. It's the delta, the difference, that matters for the flow.
okay, I think I'm getting the distinction. Temperature is the state, heat is the flow because of a difference in state.
That's a really good summary.
And since heat is energy transfer, we measure it in joules.
Yes, the SI unit for energy, including heat, is the joule. Yeah, you'll definitely see other units too.
Like calories.
Right, the calorie count. And the kilocalorie, kcal, which is 1,000 calories, that's the dietary calorie with a capital C you see on food packaging. There's also the British thermal unit, B2, used a lot in engineering, especially for heating and cooling systems.
Lots of units, but all measuring energy transfer.
Correct.
Okay, one last thing. Can internal energy be changed without heat transfer? What about doing work?
Good question. Yes, absolutely. Work can change internal energy. Think about hammering a nail.
It gets warm.
Right. That's friction doing work. Mechanical energy you put into overcoming friction gets converted mostly into internal energy of the nail and the wood, increasing their temperature.
Or stretching a rubber band quickly.
Yeah, try it. Stretch it fast and touch it to your lip. You might feel it gets slightly warmer. That's the work you did, stretching it, increasing its internal energy.
So work is another way to change that internal energy.
It is. And this all ties into the fundamental principle of conservation of energy.
Energy can't be created or destroyed.
It just changes form. When we account for changes in internal energy along with changes in potential energy and kinetic energy, the total energy of an isolated system remains constant. So PIP plus DE plus DE equals 0.
Even if mechanical energy seems to disappear, like when friction slows something down?
It's usually just been converted into internal energy, often showing up as a temperature increase. It's not lost, just transformed.
Wow, okay. That connects everything back nicely. So let's recap quickly. We started with the feeling of hot and cold, but saw that temperature is really about the average kinetic energy of particles.
And when objects are in contact, they exchange energy until they reach thermal equilibrium, the same temperature.
We measure temperature using thermal expansion, often with scales like Celsius, Fahrenheit, or the absolute Kelvin scale, which starts at absolute 0.
Right. And heat, crucially, isn't temperature itself, but the transfer of energy because of a temperature difference, always flowing from hot to cold.
And finally, internal energy can also be changed by doing work, all governed by the conservation of energy.
You've nailed the key points.
Excellent. So time for a quick reflection question for everyone listening.
Okay, here's one to think about. If you touch a metal doorknob and the wooden door it's attached to in the same room, why does the metal usually feel colder even though they're both at the same room temperature? Think about our discussion on the sense of touch, temperature, and maybe a little bit about heat transfer properties.
Great question. Something to mull over. Okay, that wraps up our deep dive for today. Stay in contact with your physics teacher, stay creative,